We're starting a new chapter on chemical calculations, chapter 9, and we're opening up our chapter with a discussion about the mole. What I'll do is I will put the notes under the camera and wait a few seconds so that you can pause your video so you can copy those down, and then I will talk about the notes. Okay, so I assume you've copied your notes by now. So we're going to talk about the mole, and this is section 9.1 in your textbook, Avogadro's number and the mole. The mole is the amount of substance contained in 6.022 times 10 to the 23rd particles. This number, 6.022 times 10 to the 23rd, is called Avogadro's number. Avogadro was an Italian scientist who discovered the volume of gas that contains this number of particles. And this is a really big number. This is 602.2 sextillion. This is such a large number that it's only used for very small things like atoms and molecules, because if we were to use it for something like bricks or golf balls, we have never even produced this number of those items. And to give you an idea here of how to use this number, 1 mole of helium atoms equals 6.022 times 10 to the 23rd helium atoms. 1 mole of water molecules is 6.022 times 10 to the 23rd water molecules. 1 mole of sodium chloride formula units is 6.022 times 10 to the 23rd sodium chloride formula units. So whenever we say we have 1 mole of something, we always have 6.022 times 10 to the 23rd of those items. That number never changes for a mole. It's not like a dozen. If I have a dozen donuts, you know I have 12 donuts. Well, if I have a dozen chocolate-covered strawberries, I also have a dozen 12 chocolate-covered strawberries. The amount of a dozen does not change. So a mole is a lot like a dozen, but it's a much larger number than 12. So because of that, the mole is both a number and a quantity of matter. A mole represents Avogadro's number of particles, and it also represents the quantity of matter in Avogadro's number, thus providing a transition between the number of particles and the quantity of matter. And we need to have a number like this because the particles are so small. Actually, I was just listening to FLN on the radio this morning, and they were saying that 10 drops of water contains as many molecules of water as there are stars that we know of so far in our universe. So this is how small those particles really are and why we need a unit to help us count them. Now, some calculations we might see when we do this. I'll give you a few seconds to pause your video and copy these problems down. Okay, so one question you might be asked is, how many atoms are in 4.5 moles of helium? Now, to do this problem, we're going to go back to our bridge notation. So we're going to be doing unit conversion for this. And so to set up this problem, we start out with our 4.5 moles of helium. And please put the helium down because we're going to be using this in different ways, and you'll see why this will be important later. And we want to go from moles to atoms. So we know that 1 mole of helium contains 6.022 times 10 to the 23rd atoms of helium. Okay, remember, when you're setting up your problems, you want your units on the bottom to cancel your units on the top. Then you know you've set your problem up properly. And so when we do the multiplication, we find that in 4.5 moles of helium, there are 2.7 times 10 to the 24th atoms of helium and 4.5 moles of helium. So it's just our bridge notation and cancellation. Let's take a look at the next problem. I'll give you a few seconds in case you haven't copied that down. How many moles of aluminum are in 1.20 times 10 to the 24th atoms of aluminum? So much like the other problem, we start with what we know, 1.20 times 10 to the 24th atoms of aluminum. We do our bridge notation. We want to go to moles. So we know if we have atoms on the top, we need atoms on the bottom. And we know that there are 6.022 times 10 to the 23rd atoms of aluminum in 1 mole of aluminum. So in this case, we have to divide 1.20 times 10 to the 24th by 6.022 times 10 to the 23rd. Now notice I canceled out my units, and when we do that, we find that there are 2 moles of aluminum when we have 1.20 times 10 to the 24th atoms of aluminum. Notice this is the label we're after. That's the label that goes here. Just like up above here, what we don't cross out becomes our label. So that is it for this section. I will make a separate video for the next section, even though it's still part of your work for today.